All right, guys, we're starting a new chapter on multiplexing, CAN bus communication, stuff like that. So as always, please access your Canvas, download the study guide, follow along. It's definitely going to help filling out those blanks. You know how it goes. So right off the bat, we've talked about multiple different types of signals, analog signal versus digital signal, digital signal, right? So analog signal, you have a constant output voltage, whether that be a sensor sending a signal back to the ECM or whatever. You'll always have a voltage return. So here we would have, I don't know, 3 volts. Here we would have 6 volts. Here we would have 8 volts. Here we'd have 12 volts, and so on and so forth. Digital signal, once again, we kind of talked about this, especially in pulse width modulation. You have on versus off time. So here you have 0 volts. Here you may have 12 volts. Here you have 0 volts, 12 volts, so on and so forth. So in pulse width modulation, on time versus off time determines the source voltage that is received, right? So the ACV, if the on time versus off time is 50% of the time, and the receiving component is looking for, or it doesn't matter what it's looking for, it's going to read that as 50% of the supplied voltage. So if the ECM, let's say, was supplying 5 volts, then 50% of that would be 2.5 volts is what an air control valve may read, which means it's only going to open halfway because it's getting half of the possible voltage. So in communications, we're using the same type of signal, the square wave signal, but we're not actually working the same way as in pulse width modulation. So an air control valve, it receives that 50% because that's what it understands. It understands half voltage. It doesn't understand on, off, on, off. Well, now the receiving unit in communications, because we're talking between computers, right? So the receiving unit's another computer. So a computer can actually understand off, on, off, on. And they're actually going to read it as 0, 1. 0, 1. I don't know if any of you have ever heard of binary code or not, but that's what it is. It's 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, and it really doesn't matter. Let's say, for example, that list of zeros and ones I just sent off, that may be telling the engine RPM to bump up a little bit, right? So a computer has its own language of zeros and ones, and every receiving computer shares that exact same language of zeros and ones. Now we can communicate with zeros and ones, which is red. Voltage off, voltage on, voltage off, voltage on. That's communications, and that's what we're going to delve into here in the next few slides. So frequency, that's definitely what we need to talk about right off the bat. So once again, in pulse width modulation, frequency changed versus amount of on time versus amount of off time. So right here in this first section, we're going to see 50% on, 50% off. That's going to read as half the supplied voltage. Whereas back here, we're going to see 1/3 of the time on versus 2/3 of the time off. So this actual supplied voltage is going to be read as 1/3 of the source or the supplied voltage, right? So if it was 12 volts max, then we'd see 6 volts during this entire section, and we would only see 4 volts during this section, right? Because that's 1/3. Okay, so let's talk about communications though. So in communications, remember we're talking zeros and ones, right? So right here we're going to have a 0. Here we would have a 1. Here we would have a 0. Here we would have a 1. But back here, you notice the frequency's changed. It's wider. Well, all timing is the same, and that's a very important factor, and we're going to definitely talk about this later when we're talking about communications. Timing is critical. But for right now, what we're looking at is if we can assume they're all on the same time, we're going to be looking at 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, right? And so on and so forth. So if we ever see a section where it's just off for this entire stretch, then it's going to be 0, 0, 0, 0, 0, 0, 1, so on and so forth. All right, so that's frequency in communications. So what exactly is multiplexing? We talked about, it's numbers being shared between computers so far, but what is communications? Why is it important? So we need to share data, right? Let's take, for example, I don't know, any vehicle, so a car. a car communicates on multiplexing right now, CAN bus lines, right? Um, if the driver steps on the brakes, and everything's in a computer now, right? So your lights, your brake lights go through a computer. They're turned on by a computer. So if the driver steps on the brakes, then we need to be able to communicate a message from the brake, or not from the brake pedal, but from the body controller to potentially whatever other controller controls the lights, to the transmission to tell the transmission, hey, you need to downshift, to the engine, hey, drop RPM, we're slowing down, right? So all this different stuff has to communicate together. And so basically what happens is the body controller, which is in control of the brake pedal, right, is going to send out a list of numbers 000011001100101010. And that's going to tell every single other computer, hey, the driver stepped on the brake. We need to slow down, right? We need to let other people know we're slowing down. Let's kick on some lights. Let's drop the RPM. Let's downshift. Let's do all this stuff that is necessary to slow down. That's communications, and that's the essence of multiplexing, is that everything has to be able to talk and understand each other at the same time. I mean, we've moved from our vehicle systems to having 0 computers up to having 2 to 3 computers to now some of them have 30, 40 computers on their one vehicle. I mean, that's going to be your combines and stuff like that, but they're there. There's 30 or 40 different computers, just like the laptop sitting in front of you, that are talking to each other. So all of these have to be able to communicate at the same time and at the same message. Um, many technicians, almost every single day, there are a few that do not get much into this diagnostic, but many technicians every single day, every time you hook a computer up to a unit, so you've seen that little round plug, or sometimes they're square plugs depending on what OEM and what can you're working on, and so on and so forth. We'll get to that later. But when you talk to a unit with a computer, you are accessing, or you are gaining access to what's called the CAN bus, or the communication bus, the multiplexing unit. There's tons of different names for it, right? And you are literally talking to every single one of those computers at the same time. All right, so binary system. All right, so the original binary system, the original communications, the nice and slow communications, right? You guys remember the computers way back in the day. Well, this is even a little bit back before that. We're talking, it took hours to just turn on the computer, much less actually bring up any type of page, right? This is the original binary system. So binary is usually read in 16-digit codes, right? So this is digit 1, digit 2, digit 3, digit 4, so on and so forth. So to write one 16-digit binary number, which is one little communication, so let's say the letter A takes 16 bits to type the letter A and to tell the computer you are sending it letter A. 16 bits of information. Now, if you look at this, 1, 2, 3, 4. That's the first 4 digits of a binary number. 5, 6, 7, 8. That's the next 4 digits. This communication is going to take a long time, right? If every single digit has to be read on one wire, then it's going to take a long time. So then we started doing some parallel linking. This definitely sped up time substantially. And what we did is we started communicating each set of binary numbers on a different wire. So this set of binary numbers can now be transferred 10 times faster, well, 4 times faster currently. This parallel linking definitely increased time. Now, eventually, we're going to get it back down to 2 wires right now, but parallel linking is what brought speed up originally. After time, we started adding in more transistors into our ECMs, and we've talked about transistors before, right? They're the little electronical switches inside of an ECM. That made communications that much faster. We were able to back it back down to 1 wire, and then now in communications, we actually run on 2 wires and a shield, which we're going to talk about those 2 wires, and we're going to talk about the shield. But all the same, parallel linking, obviously you can communicate faster, as well as increase in technology, as always, especially those transistors, right? There's millions of them now in every single computer. We have 30 computers on one unit. So we're talking 30 million different transistors all communicating one signal. This thing is crazy fast. The newest system communicates at 500,000 bits per second. That's a lot of bits. That's a lot of zeros and ones in 1 second. So, by the way, I should make this mentioned. This one little zero is a bit. This is a bit. So there's 16 bits in one binary number, right? So we can communicate 500,000 zeros and ones in 1 second. All right, so obviously multiplexing, for it to work, it has to communicate in a common language. That common language is bits and bytes, zeros and ones, right? It also has to communicate on the same highway. So in other words, for all these different computers to communicate, they all have to communicate in one central location. You can't just have, you know, the ECM communicating with the transmission, and then the transmission communicating with the brakes, and then the brakes has to communicate with only the engine. I mean, it doesn't work that way. So they all have to be able to communicate together, which means there has to be one highway or one data bus that all these different units can communicate on. And guess what? That's what we're getting into in like 2 more slides, right? How is that possible? But let's get there. Just remember, for now, they have to communicate the same. They have to communicate on the same highway or the same network, right? Finally, what's the advantage of doing all of this? I mean, why do we need all these different electronic controllers in these communications? Right off the bat, it simplifies our hardware. And what is hardware? It's actually the computers and the wire and all the different sensors on the unit. Now, yes, they're getting more expensive because they're smart. They're computers now. They're laptops, right? All this different stuff is laptops now on these vehicles. But what it does get rid of is it gets rid of miles and miles and miles of hard wiring. Now, you think about the actual component of wire and you're like, oh, that's silly, just taking wire off a truck. But, you know, when you start talking about actual fuel mileage on a truck and you take off miles of wiring, that's a lot of weight. And as we discovered earlier, the difference of 0.1 mile to the gallon in an over-the-road truck is the difference of almost $2,000 a year per truck. So I mean, that's a lot of money in fuel, right? That's a lot of money. So multiplexing definitely eliminates a lot of wiring. So you get into the industrial fields and stuff like that, you don't want these huge harnesses running outside of the cab, right? So let's say, for example, a forklift or something along those lines. Moving components. You do not want a bunch of wires. That's increased chance of failure. So now we're communicating down on just 2 wires. All these different laptops are communicating on 2 wires. And that greatly increases the longevity of this unit. All right. Reduces the number of in and out pins, less wires, less pins going into the modules, right? And optimize vehicle operation. Believe it or not, it's faster. Any electrical signal is faster than any mechanical signal ever given. I mean, it's just fact. Electricity travels dang near the speed of light. That's just instantaneous, right? You step on the brake pedal, the lights come on, right? Took you longer to actually step on the brake pedal than it took for the lights to come on, substantially longer. Lights are instantaneous, and they're a good example of electricity and its speed of travel. All right, so we've talked about what it takes. It takes wires, right? It takes wires. We've got to communicate on wires. It takes an actual communication signal that is all the same, zeros and ones. Finally, we have to actually designate who's going to send a message, who's going to receive the message, where's the message going to get sent, and what is the message, right? So automatically, any computer at any time that sends a message is known as the server, right? So they are serving the message to whoever. Now, the data backbone, so the sending unit serves the message onto the data backbone, right? And the data backbone is the pathway. Now, a client is going to be the receiving end of this message. So the client can pick up that message if it chooses to, Whereas if it doesn't pertain to them, so let's say, for example, that